Thank you very much, Namhoon. I'm very glad to be here and be given this chance to practice a little bit and talk about this project. Of course, this would not have been possible without Namhoon's supervision and help, so I'm very grateful for that. And if you are working with him on your PhDs, you are very lucky to have him as your supervisor. So it's one of those things to take into account. As Namhoon has said, during my last months at Cranfield University, I got the chance to work on the terrain following problem. It was a bit open at the beginning because, um, as you can see here, we're going to be focusing, the main topic is, of course, safety because you're flying very low to the ground, the knowledge that you're working with, so what information do you have to avoid the obstacles, and also prediction. And the main point of prediction is because um, we focused this problem on fixed wing aircraft. And therefore, it's not, you cannot maneuver on the spot or hover if something is uncertain and you're unsure of where to go. And you need to anticipate yourself to the movement that you must do, especially if you're flying very low to the ground. So you cannot work on a feedback and reacting to a past action, but you need to get ahead of yourself and plan your maneuver before you get there. Um, the full title of the work that we have submitted to control engineering practice is Dual Stage Risk-Aware Predictive Control System for Terrain Following using unmanned aircraft with rangefinders. Um, and we will talk later why we use a dual stage system. But the main point is that we want to combine a digital elevation model data, so prior knowledge of the terrain, with onboard measurements. And this combination is first done uh, on a longer foresight, still a moving window, but a longer foresight and a longer prediction horizon, and then just a shorter prediction horizon for the control of the nonlinear dynamics of the aircraft. Um, yeah, we will go a bit quickly through the introduction, but we will stay a little bit more on the methodology and the results that are quite interesting. So what this was about was the main point of the work that we did was to develop a terrain following capability. And it was specifically for Tier 1 UAS, so smaller, lightweight aircraft. Thereafter, it must be also cost effective. This must not be a very expensive system, such as those that we might have seen on older and larger fighter jet aircraft, such as the Panavia Tornado or other cruise missiles that are much more expensive. But if this must be integrated in a platform that costs less than $20,000, for example, the system should not be expensive, should be able to run in simple enough hardware that you could find or computer and processors. We were also quite keen in investigating how the system, because once you have implemented a control system, how does the system react to the uncertainty of the knowledge that you have gathered? So you've got a digital elevation model, you've got obstacle measurements, but those measurements and that model is incomplete. You don't have the whole picture, and you might not trust a lot those measurements. So how does that uncertainty affect the performance of the terrain following system? And lastly, given that we have developed this system, are there devices out there off the shelf that we could use that could give us good enough performance, at least theoretically, by the specifications of the manufacturer? So, well, let me get back. Yes. Given that this is a fixed wing UAV, we've got to consider the longitudinal dynamics problem mostly, although this system can be expanded afterwards to the full three-dimensional dynamics, the 6 degrees of freedom, but we have started with just 3 degrees of freedom for the longitudinal ones. We are going to be using model predictive control. That's for the prediction stage to handle the nonlinear dynamics. And lastly, the first part is that we are using a cubic basis spline envelope to combine the digital elevation model and the sensor measurements that we are performing online. And we do so in a risk-aware manner because, as I said before, you might not trust a lot those measurements, so we are implementing chance constraints at the same time to combine this data. As we have gathered, this is the first work on terrain following that is combining those two uncertain measurement points on a risk-aware and in a real-time manner. So that was the main point of this work. The first one was to separate the terrain following problem in not just a single algorithm for guidance and control, but two stages. The first stage would combine the data and would provide a long horizon in a simpler manner. And the second stage, in a close-up guidance and control, would provide with MPC, would provide the commands to control the aircraft and handle the fast nonlinear dynamics. Um, Maybe if you have studied a little bit on terrain following, this might be familiar, maybe not. There are certain key abbreviations. So when talking about terrain following, proper TF, this is just the vertical avoidance. And when speaking about terrain avoidance, this talks about lateral avoidance. So this is the second part of the problem that has not been tackled but could be expanded. That is how to plan the trajectory on a 3D manner, not just a 2D envelope. And then we've got inside of terrain following, when flying at very low speed, low altitude and high speed, this is called nap of the Earth. So you are just hugging the Earth. And this is quite interesting for fixed wing because you need to consider the dynamic feasibility. And then there are several options here. So you can use geometric and optimal control theory for the trajectory pre-computation. But this is based only on digital elevation model data. So if something that was not in the DEM, the digital elevation model, appears in your flight path, you will not be able to react to it because it was not planned. Or you could use just the sensor measurements with real-time prediction horizon. But this has another problem. If you're just using sensor measurements and you're not using a DEM, you cannot react to information that you do not yet know. So for example, you might be climbing a hill and your controller will not be able to plan the pitch down maneuver after it overcomes the top of the hill. So you've got occlusion and you cannot handle that occlusion because you just have your real-time measurements and they are blocked by the first object that they encounter. So those pre-computed paths um, can lead to danger when incomplete, but relying only on sensor measurements, also you could find yourself with an inevitable collision state when suddenly you've got to plan a maneuver that you did not account for. So to do this, we will need both a digital elevation model, real-time onboard sensors, and also real-time processing to handle this information. And this is the main gap, as I said before, in this research right now, that's how to combine the digital elevation data with onboard and online inputs. Let me talk a little bit about digital elevation models and direct ground mapping. We've got two kinds of digital elevation models. You could be talking about digital terrain models or digital surface models. The digital terrain models do not include obstacles that overcome the bare ground of the Earth. So you've got buildings, cars, trees. Those would not be taken into account in digital terrain models. And then you've got digital surface models that do include those kinds of obstacles. Either one of the two that you choose to work with will have incompleteness. Even if it's a digital surface model, it will have obstacles that were not included because they have changed position, because the trees have grown, some trees that were there have been knocked over. So even though the digital surface model could seem interesting and you could consider that it has all the information required, if you're flying, let's say at 5 meters altitude, you cannot work with that. You cannot take that and trust it. And then you must choose what type of digital vision model that you want. You could go for a global DM, but this does not have the resolution that you are looking for because you would have a data point every 200 meters or so. And then you could go into elevation models that have been built with radar scans and LiDAR scans. Both of those start to be good enough already to be used. Um, the issue is that radar scans, although they have, you could work with its data quality with the horizontal spacing between points, 5 meters. The vertical error that you're going to get here, the uncertainty that you're working with, will be about plus minus 3 meters. In standard deviation would be 1.8 meters approximately. But LiDAR DMs, those are already very good and very precise with the information that they have and that they take into account. So you're gonna have a very good accuracy on the terrain estimation, but on the terrain estimation that is included. Unknown obstacles not included will not be in there. So even though it is advertised to have a very small vertical error, we are talking about centimeter level. If there's a tree that was not in there, you're gonna have a problem. So even though this would be the most recommended DM to be using, um, but we must take into account that the data, because it is very compact and it is very detailed, it takes a lot of memory to store all this data. So this would go a little bit against the computer processing requirements, but there can be workarounds with that. It would be the most recommended. And then we have the second problem of the second source of information of our system. As we said, we must combine a digital vision model with onboard measurements. Um, these work in these two data sources are completely different. One is static, and you cannot change the size of it. The other one is online. You keep measuring new data. You keep gathering new data as you move forward. And there would be several options. You could try to implement a SLAM technique here, for example, in which you might want to simultaneously locate yourself and map the environment at the same time. Critically, the SLAM technique relies on landmarks. So if if you must rely on a landmark, that means that you already have a little bit of knowledge that you're going to encounter certain landmarks and you're going to build your map around there. And then if you do several passes over the same place, you can improve your estimation of your environment. But if this is a low-cost terrain following technique, mostly it might be applied to incursion or stealth missions where you do not want to be avoided, and you will not probably go over the same place twice. It loses its point because you want to find obstacles that you did not know previously. So you cannot rely on landmarks because you might not have those landmarks in your DM, and those are very small landmarks because we could be talking about trees, buildings, anything above 5 meters could be a danger for the aircraft. And thereafter, we have settled on direct ground mapping. This way, we are propagating uncertainty because the direct ground mapping, we measure the obstacles based on our own estimation of our position. So if we know the position of our aircraft, AXZ position vertical, and we've got a rangefinder sensor with a certain look down angle that measures a distance, we can estimate the position of our points. And this is a very fast and a quite efficient way to gather a cloud point data set of the environment of obstacles. We have this issue that the uncertainty, the estimation is propagated from our own estimation of the position. So we must look into how do we estimate the position of the aircraft. And here we might also choose several factors. we could look into mostly for cost efficient GNSS, INS fusion techniques. And in here, the most standard, most common one would be loosely coupled Kalman filters, because you can work with those even if the quality of the GNSS is not very good. And um, you could have updates not periodically and every while. On here, if we can also work with with differential GNSS, so real-time kinematics, we can much improve our performance. And nowadays, if you look through the internet, we can find many uh, RTK GNSS sensors for a very affordable price. So, and those ones can work up to 40 kilometers. So it's a good option. And lastly, for our measurement sensors, we must choose between radar and LiDAR. So there are radars to be installed in small UAVs for range finding, and there are also many more LiDARs out there. So the radars would provide a better capability for all weather operations. The LiDAR might be occluded or interfered with if there's fog or if there are particles in the air, those can hinder the LiDAR. But the LiDAR has a much better angular resolution. Gathered that the difference in the distance uncertainty between radar and LiDAR is not much, but the angular uncertainty between a radar and the LiDAR is quite critical, and we will look into that later. Um, so now we are going into why we must use model predictive control. So given our knowledge that we are working with a fixed wing aircraft, and we must be quite precise in our maneuver because we are following very low to the ground, we must think and we must consider that those are nonlinear platforms. The dynamics are nonlinear. And also it's an underactuated system. So if we are talking about the 6 degrees of freedom, we might have less less control inputs than degrees of freedom. And the same happens in the longitudinal problem, where we have 3 degrees of freedom, so forward movement, vertical movement, and rotation. But we just have two control signals, that is the elevator and the thrust command for the aircraft. If we were to use linear model predictive control on a nonlinear underactuated platform, the tracking is not very good. We cannot precisely follow our desired trajectory with linear model predictive control. Even though it has advantages, you can have you've got assurance. The convergence is assured because it's a convex problem, and it can run very, very fast. So it's a very efficient problem if you are just using quadratic programming. The performance that you're going to get in a nonlinear undirected platform might be unacceptable, especially if the aircraft is at risks. So even though it's going to take more time to compute, it is better to consider nonlinear model predictive control for a fixed wing aircraft, because you're going to properly be considering all the nonlinear dynamics and not just an approximation or linearization of those around the trimming point. And because you might do a very harsh maneuver and a pull-up maneuver, you're going to get out of that trim point quite frequently. So it's not acceptable. In this case, the performance that we can get with nonlinear model predictive control with underactuated platforms is substantially better than linear model predictive control. And that's why we choose it. If you want to study or research with nonlinear model predictive control, there are several libraries out there that that I can recommend. The one that I've worked with is Casadi. You can use that directly with Python or or directly in C code if you want to compile it. But you've got other options if you want to deploy it on hardware, on real systems, and test it in your lab. You can use Akados or Panoc. Those are lightweight libraries that use compilers specifically designed to do point-to-point operations and not and avoid matrix operations as Casadi does. So those can be implemented on simple STM controllers and work much more efficiently. But that would be for further research. But it is nice to have a reference on where you can get some of those algorithms off the shelf that you can work directly with after setting them up. Um, let's talk a little bit about maybe the interesting part after having placed you into context. I hope it's not too dense or I'm not going too fast. Um, this is a dual stage system for terrain following, and as I've said repeatedly, um, we've got the first stage that's gonna combine the data, the DEM data and the direct ground mapping data, and it's gonna do so through a cubic basis spline envelope. So this is the perception and path planning stage. And after this is done, we get the guidance and control stage that is handled by an NPC. So what is happening, and we can see this a little bit in this diagram initially, is that we've got the blue points. Those would be the DEM points that we have gathered. And then through our rangefinder, we have measured some yellow points as well. Those would be the two data inputs, the DM and the direct ground mapping. So once we've got those 2 points, we will craft an upper envelope above those. That will be the orange line through the orange points. And because as I'm going to be explaining later, this is going to be a convex problem. We have formulated as a convex problem. We can solve it through a quadratic program. The thing that we said before that is not good. It's not acceptable right now to handle nonlinear underactuated dynamics. It is good enough and it is efficient and fast to handle a large data set of points and plan an upper envelope. So we are going to take advantage of the efficiency of the quadratic program to build a cubic basis spline envelope above these 2 points. After we have crafted this in a much shorter prediction horizon, we can use the NMPC so that the UAV can control and can plan a trajectory above the envelope that we have just gathered. So we've got these 2 stages and we are dividing the problem. We have a first stage that handles the 2 different sets of data, the 2 different time scales, because we are gathering data very fast, but we can afford to provide a longer prediction horizon. And then a second stage on a shorter time scale where we must handle the control of the aircraft. And we do not need the aircraft to plan, for example, 10 seconds ahead. For 2 seconds, it is enough to properly condition flight, a stable flight on a fixed wing platform. And well, as you can see here, the states are quite standard. So we've got airspeed, angle of attack, pitch rate, the pitch angle and the position. You must include in your states the position of the aircraft because it must take into account where this aircraft is relative to the envelope that you have just crafted. So if you were just trimming the aircraft, you might not need to include the position in your states for the NMPC, but because you need to know the aircraft relative to your envelope, you must now include the position as a state directly for your NMPC. And just a curiosity, we used a model. We used a full model with stability and control derivatives from this small UAV here. This is the Skywalker UAV. And there are some works out there that have done system identification on this craft. So it was, because it is quite popular and quite common, we used it as a reference to develop the system and test its performance on what would be a low-cost aircraft. We need to test it somewhere. So what we did is that we generated randomly our own terrain through Diamond Square fractal algorithm. This just generates realistic looking terrain. It's quite simple. After that, you can get a synthetic elevation model with a little bit of uncertainty that you could extract from the ground truth that you have randomly generated. And then we can, over that, we can do our own simulations and introduce introduce rangefinder measurements. In this case, we did it at 50 Hertz, but this can be modified. And the NMPC is going to be run at a lower scale. As I said, we are combining different time scales. The NMPC runs at 10 Hertz. So you've got to handle this difference in the prediction scales, the horizon scales, and also the compute scales for the system. As I said before, the issue here with direct run mapping is that we are propagating uncertainty because we are working based on our own current estimation. That said, if we apply Taylor through the equations that we got, and we can get both uncertainty propagations, the critical thing is the vertical uncertainty. And if we consider that the aircraft is more or less level and the rangefinder is also quite level, it is propagated to the distance square with distance. So if you've got a little bit of angular uncertainty, this is going to be converted and propagated into a very large vertical uncertainty through the distance. And this is the main problem that we are going to be encountering later on. When we craft, this is the first stage of our system. When we craft the envelope, we are going to be doing so with cubic basis spline. Why do we do it like this? Because we can modulate the aggressiveness of this trajectory. Because it is cubic to the third order, we can reach the second derivative, and we can penalize in our cost function to fit through a quadratic program our basis spline. We can penalize the aggressiveness, and we can that with the fitting. So in these two cases, we have provided an example of what would be a high aggressiveness envelope with the red line, which fits very closely to the obstacles that you have measured. Or we can lower the aggressiveness and provide a smoother trajectory over the points. So it enables us to provide, first off, a convex problem, less dataset points because you can use fewer points to craft your cubic basis spline envelope as a combination of basis functions. And we can modulate the aggressiveness. So doing all this in a moving window and with convex formulation, so we don't need to include here a nonlinear term, this can be solved very, very fast, and it's a good way, an efficient way to provide a longer prediction horizon around the aircraft. Importantly, the prediction horizon for the DM obstacle envelope is not done straight ahead from the UAV position to a certain distance, but we must include a certain envelope, a certain envelope behind the aircraft. This is one of the key points that will help us to navigate, because once an obstacle is overcome and we are doing the pitch down maneuver after overcoming an obstacle, we still need a reference trajectory for descending. If the envelope was only starting only from the UAV position after the obstacle has been overcome, we would lose that reference and the UAV would do a very aggressive pitch down maneuver suddenly. So this is also one of the key points. And here is another point where we can implement our risk-aware formulation. So what is happening? Given our dataset points, you might have some points that are above. You have overestimated the height of the obstacle, some points that are underestimating the height of the obstacle. So doing standard chance constraint formulation, you've got three possible scenarios. You can work with a low risk, neutral risk, or a high risk scenario. In a low risk, you should only use this scenario if you consider that all the points are beneath all the points that you have measured are beneath the nominal height of the obstacle. So that way, the envelope is gonna raise the obstacle envelope, so you avoid a crash. So this way, you're gonna be providing a lot of over provisioning, a lot of security, a lot of safety, but this is not optimal because you're gonna be flying much higher than you might need to. Neutral risk is going to adapt, the envelope is going to adapt itself, and it's going to be fitted just above the tallest point that you have measured. But if you do a high risk, you will be considering that some of the points that you have are above the nominal height of the obstacle, and therefore you can you can lower the envelope a little bit, even though you're increasing the risk, but you're gaining a little bit of performance. And this parameter can help the system to modulate itself depending on the mission and depending on the quality of the sensors that you are using. So if you're using a very uncertain sensor, as we will see later on, we can work a little bit with the chance constraints and the risk allowance that we give the system to increase a little bit the danger of our flight trajectory, but improve the performance that we have lost through this sensor uncertainty. And as we said also previously, this is now the second stage of the terrain following system. The guidance and control stage is handled by the model predictive controller. And this does not need to be a very long prediction, can be a close-up guidance. And it is working above the points that we have generated from our envelope. And we have just used direct location with multiple shootings. So at every point we have a state and a control prediction that we have optimized. And for terrain following, you might want to develop your cost function as a combination of the envelope altitude. You are tracking a certain altitude. You're also tracking a certain speed. You don't want your system to deviate a lot from your reference airspeed to avoid a stall or to avoid going very fast. And then you want a smooth and well-conditioned flight. So for that, you must penalize the control rates. You don't want your elevator and throttle fluttering. So you want to penalize here your control rates. But importantly, the control rates depend on different time steps. It is more efficient to include the pitch rate directly as a cost in the function because it depends only in its current state. And penalizing the pitch rate, you're already indirectly penalizing the control rates, but it's going to help the system to move faster. So you can include both, and this improves the computation of the system. And thereafter, it's quite, the constraints are quite straightforward. You've got the nonlinear dynamics. You are limiting a minimum and maximum altitude above the terrain in which you're flying. And also you are limiting the control envelope, the inputs. There's a certain range of elevator angles and thrust settings from 0 to 1. And also you've got a flight envelope for the states of your aircraft, which you cannot get out because you would start to feel stall effects and nonlinear effects that you have not yet considered into the equations for the dynamics that you have built. If we put all this together through Casadi, as I've said, when compiled, we can get assured compute times below 60 milliseconds, and for a 10 hertz control loop, that would be enough. But recently, I've gotten compute times of just 10 milliseconds, and this is on a very simple CPU chip, an Intel N200. That's just about 1 gigahertz clock speed. So it is quite impressive the optimization that one can reach if the MPC is well defined and the variables are properly structured. As I've said, once you compute this, you will be able to get a prediction, a certain prediction horizon. These are the different states that we've got, but critically, I want you to look at the altitude, and we can see that initially it has predicted the pitch down maneuver and then start to hug the terrain. So the aircraft will first drop down, and after that, it will start to follow the terrain that we've got here below. For example, this would be just a single instance, a single prediction horizon, and what the MPC is going to be doing. The prediction horizon here, we are only showing 4 seconds of the prediction horizon. We are usually computing this in flight with 2 seconds, but the DEM envelope that is shown here, this is just a little stretch of the envelope, whilst this usually comprises 10 seconds of the flight time. And let me show you what happens here. First off, this would be the maneuver of a system where it does not have a DEM obstacle envelope. So suddenly the MPC must do all the work, all the smoothing, and it is quite hard on the system. So because it cannot plan the pull-up maneuver until it reaches almost the obstacle. It is a very harsh, very aggressive maneuver, and it takes a lot of compute time, and many times the solver might stall. So here the solver is stalled, it is not converging, and it is still going up, and now it's found another solution. This is not optimal. All the work must be done in the guidance and control stage. And to provide a smoother control, we would need to increase this prediction horizon several times. In previous work, the prediction horizon for this kind of terrain following system, where the MPC must do all the work, is about 10 seconds. In our case, we want to work with just 2 seconds and give the 10-second prediction horizon to the first stage, that is the DM obstacle envelope. And this can be seen here, whereas as we get the points, the pull-up maneuver now starts earlier, and we can evaluate the obstacle height earlier, and look at here how the envelope grows as we gather more data, and our aircraft can smoothly follow the trajectory without a sudden aggressive maneuver. So dividing this problem into 2 stages, we are actually taking advantage of what can be quickly computed and fusing the data, and then just using the MPC for a single task, that is the guidance and control of the aircraft, not including and not combining data and obstacles at the same time. And just using the same MPC parameters as before, we are getting a much better performance without any non-convergence failure of our solvers. But then again, like if we now have some obstacle uncertainty, we can now see that the points that we are measuring are quite randomized, and the points, some of those are below the nominal target, but some of those are above. And because some of those are above, and this is an upper envelope by definition, we are going to be flying higher than we need to. This is with neutral risk, so the envelope is fitted just above the highest point that it has found. This, although safe, is not optimal for our flight if we want to still get the same performance as we were getting on a nominal scenario without uncertainty, but using our real sensors that have uncertainty, maybe quite a large uncertainty depending on the day or the environmental conditions. What we must try to do here is to analyze what is the most critical stage of that uncertainty. So these are several trajectories with different degrees of uncertainty. In this case, this is the digital elevation model uncertainty. And actually, if we compare the root mean square deviation from the baseline envelope, the deviation of the trajectories, with the growing DM uncertainty, we can see that it is quite linear. Like for 175 meters of uncertainty, we get almost 1.5 meters of standard deviation on our path tracking. So there's this linear correlation between vertical positioning uncertainties and the performance that we are getting. And well, as you can see in the trajectories, the higher the uncertainty, the higher the envelopes are. You can see that over the obstacles, there is no difference in the trajectories because this is uncertainty only applied to the DM. Over the obstacles, there is no DM data. All the data comes from the sensor. And because the sensor at this time is perfect, the trajectory overcoming the obstacles is also perfect in both cases. But, well, also, this effect, if using a radar DM, it's still not critical. You could still work with a radar DM. Just you might be flying sometimes 2 meters higher than you need to, but it is not such a bad performance degradation. When looking now at the obstacle angle uncertainty, this is the most critical stage, as I said before. Just a little bit of 3 degrees of plus minus error in a radar sensor will give you almost 4 meters of standard deviation on the tracking, and you can have peaks of up to 8 meters, almost 9 meters of extra altitude that the system must perform. And because the trajectories are much more aggressive than before, you can even start to get again those NMPC solver failures that you were seeing before the implementation of the cubic basis spline envelope. So when choosing a sensor suite for this system, you must consider that the angular uncertainty of the sensors that you're going to be using are the most critical parameter. This is the parameter to which the performance has the highest sensitivity. And even though the system currently will avoid any crash, doing those aggressive maneuvers and flying that much higher than necessary can be a risk for the mission, maybe not for the aircraft itself. If it is detected somehow and it is not hogging the terrain as it was expected. This might be a table just summarizing the different tests on the parameters that we have used, in which we highlight that the sensor angle is the most critical, while vertical uncertainties have this direct propagation. Horizontal uncertainties, horizontal positioning is not very critical. So, for example, the sensor distance, even if using the uncertainty from a radar, we get quite a low maximum deviation increase. And interestingly, the minimum deviations stay the same because we are using an upper envelope. And that means that now we can use chance constraints and we can increase the risk allowance to improve our performance, even though we might have uncertainty degradation. So in this situation, even if flying and even if our points are higher than the nominal obstacles, the envelope is gonna take that into account and take our risk level into account so that the envelope is not fit up above the highest point, but you can adjust it so that it lowers a little bit its envelope, increasing the risk, but improving the performance as you can see here. This was the same simulation with the same uncertainty parameters, but now the envelope is fitted quite more properly than it was before, even though we have worse knowledge of our environment, but we have increased the risk as a trade-off. This might be the opposite as you were saying before. So as we increase our risk allowance from 0.5 to almost 1, we can decrease our maximum deviations and our root mean square. We can use a lot of risk allowance on the digital elevation model knowledge. This is so because we have a backup knowledge. The backup knowledge, even though you lower, you might be fitting the envelope beneath the DEM points, so those ones are no longer the active constraints of the DEM envelope. The active constraints are gonna be now the points measured through the direct ground mapping. Those are becoming the active constraints because we have given a lot of risk allowance to the DEM points. And the performance is still good, so we might improve performance if you've got this backup, a good direct ground mapping sensors working behind. So if there's a certain stage of the terrain that you do not have a lot of knowledge, but you've got a good sensor, you can still regain some of the performance that you lose. But still, most importantly, you are not going to regain all the performance. As you can see here, at this point, when almost at 99 risk allowance, the DEM points are never the active constraints. The active constraints at this stage are always the obstacle measurement points. But still, you can see that the performance is not the same as when we had both. The same level would be those baseline lines here when we have non-uncertain DEM in combination with non-uncertain obstacle measurements. So this gives us information that the best performance is only achieved when we combine the DEM data with the obstacle measurement data. If we rely only on obstacle measurement data of online measurements, we are not going to be getting the same performance as if we combine the two systems, the two information sources at the same time without uncertainty. So relying on just one, even though you will improve the performance, will not get you the same performance as before. And now the most critical stage. Can we use risk allowance on the sensor measurements, on the online measurements that we do? Yes, but just moderately. As I said before, the obstacle measurement is going to be your fallback solution if there is no knowledge on the DM. What this means is that we can increase a little bit our risk allowance, but we cannot increase it as much as we did for the DM. On the DM, you can increase it to the maximum and rely on the sensor measurements on the rangefinder, but on the rangefinder, you cannot do the same, but because you cannot rely on the DM. You cannot make it so that the DM points are the active constraints only because the DM does not have information about certain obstacles. That way, as you can see here, we can start to improve the performance, the maximum deviation, the root mean square, while keeping the minimum deviation stables up to a certain point. After this stage, after the point where the obstacle measurements become the inactive constraints, you're gonna be start to lower your minimum deviations, and this means that you're gonna be placing your UAV at danger of crashing. And this is even more unacceptable than the risk of the UAV being detected. So we see here the criticality of the sensors that are our fallback information source, and we can just apply a little bit of risk allowance to improve the performance, but just moderately, while we can completely disregard the DM if we want to improve performance, but the best is only achieved with the combination of the two data sources. And as I've said before, looking at off-the-shelf components out there, we could find a combination of autopilots, IMUs, GNSS, and also as lidars, because given the sensitivity to the angular resolution of the rangefinder, we are going to be choosing lidar, even though it has other disadvantages. Having a small angular uncertainty helps us a lot, and through this we can just get a deviation of plus minus 0.30 force meters. So it's a total of a 1 meter band that you're going to be flying within for the terrain following. And this is with theoretical data sheets from the manufacturers. Of course, you should not trust and follow to the letter what the manufacturer says about their products. And after working some months in industry, I can assure you that they almost never perform exactly as specified. This is something that happens. But still, even if it has a certain degradation from this point, it is a promising performance that we can give an LiDAR and off-the-shelf GNSS IMU algorithms. We could get quite an acceptable altitude band for terrain following with this system. Just to do a recap, this is now nearing the end, but the two stages. First stage is the cubic basis spline. We are combining the DM with the sensor measurements, and this is given to provide an efficient trajectory and using afterwards a faster NMPC control on a shorter horizon. Critically sensitive to angular uncertainty. So this is the main point that we must look to and why we choose LiDAR. But we can tune a little bit the risk allowance to gain back this performance while balancing the trade-offs, especially careful on the risk allowance on the direct ground mapping measurements. We can use risk allowance without that much danger on the DEM. And from this point onward, I would like to encourage anyone into including this algorithm into other techniques. So for example, this is based on computational efficiency. So both the two stages are moving prediction windows. This does not have end-to-end path planning. So if this was combined with another algorithm that makes a first planning trajectory, and then this is used real time to avoid any obstacles found through that trajectory, it could help to improve this system, because right now, if there's a valley or there's or there's a large cliff that we are that we are approaching, this is not going to be able to detect it. We might need a longer planning to make it a complete terrain following system. This is much more for execution than for complete path planning. Also, right now, if you can recall a little bit what I talked through on the chance constraints, it is a simpler formulation in which every single point has a given risk allowance. But this must not be so, because there are certain points that, due to the nature of the upper envelope, if one point is below another, does not need to have such a weight considered. So we can look through risk allocation strategies to give each point an optimal risk allowance to improve still the performance, and perhaps solve the issue with the uncertain obstacle measurements that we have seen, that we cannot just directly improve the risk allowance. So through a smart risk allocation strategies, we can finally, we might be able to fix that problem. And also, this is a longitudinal terrain following system, but everything in this dual stage system can be expanded to the three-dimensional problem. So from cubic basis splines curves, we can then do cubic basis spline surfaces, still a convex solver. If we combine longitudinal and horizontal cubic, we can get surfaces, and we can optimize them still in a convex manner as we did. And the NMPC right now is only considering the longitudinal dynamics, but if we include also the full 6 degrees of freedom dynamics, we can also provide 3D guidance and control at the same time. So, well, up to here, this would be more or less the end of my presentation. I had not much time to modify some of the slides that I did for when I presented this work at the end of my master's degree, but I'm hoping you've still been able to follow those through, and they've been of some interest. And I'd like to again thank Nam-Hoon for all his help in guiding me and supervising this project that is still going forward right now, because we have submitted to the control engineering practice, and perhaps there is a chance to see this presented as well in the IFAC conference, hopefully. And if you've got any question, like, I'd be very glad to talk this with you, and